Welcome to today's Explainer. We're going to demystify how to build robust, reliable AI agent systems right from the ground up. If you've been following the AI space, you know we've moved way past simple chat interfaces. We're now talking about systems that can plan, explicitly use tools, and even correct their own mistakes. But how do you actually build that architecture so it doesn't just fall apart the second it hits production? Well, that's exactly what we're unpacking today.
Okay, here's our blueprint for this session. We'll be looking at the shift from models to agents, mapping out the core agent loop, diving into essential agentic design patterns, tackling the single versus multi-agent debate, and we'll finish up with memory, state, and control.
We really have to start with this fundamental question. What actually makes an AI an agent? Because honestly, a standalone large language model is basically just a brilliant consultant locked in an empty room. It's not a complete system. It's got all the knowledge in the world from its pre-training, sure, but it can't check today's weather, it can't send an email, and it definitely can't remember what you told it yesterday unless you remind it. To make it a true agent, we have to unlock that door.
Let's jump right into Section 1, from models to agents. We're shifting from passive text generation to active, goal-directed behavior.
So the crucial point here is that an agentic system is what empowers that locked-up consultant. It essentially gives them an internet connection, a calculator, and maybe even a whole team to delegate to, so they can actually drive real-world outcomes. The system transitions from just passively generating responses to active, goal-directed behavior by being embedded in a loop. It perceives, reasons, acts, and adapts. It is the literal difference between just generating text and actually generating solutions.
And this brings us to a massive paradigm shift. The model is no longer the application boundary. The prompt itself is not the system anymore. It's just one reasoning core sitting inside a much broader orchestration layer. You know, in the early days, we tried to cram every single rule, context, and instruction into one massive, super fragile prompt. But today, the model is just the brain of the operation. The real magic is happening in the architecture surrounding it. The memory stores, the tools, the control flow, the whole shebang.
To understand how that orchestration works, let's move to Section 2, the core agent loop. This is the operational cycle of intelligence.
This loop brilliantly illustrates how reasoning is explicitly coupled with action. Step 1, receive the goal. Step 2, gather context. Step 3, reason. Step 4, execute action. And Step 5, observe and adapt. That last step, observe and adapt, is absolutely crucial. That is where true agency lives. If an API call fails or a search returns the wrong data, the system doesn't just crash and burn. It sees the failure, it reasons about why it happened, and it tries a completely different approach. It learns within the task itself.
So how do we actually engineer this? Let's hit Section 3, essential agentic design patterns. This is our toolkit for control, memory, and agency. First up in our toolkit is prompt chaining. This means decomposing a complex task into a sequence of smaller, structured steps where each step feeds right into the next. We use this because single, giant prompts inevitably cause instruction overload. By breaking things down, we drastically reduce the model's cognitive load. Think of it like a giant assembly line. Instead of asking a model to read a 10-page doc, extract the themes, write a summary, and draft an email all in one go, you chain it. Step 1 extracts facts, Step 2 clusters the themes, and so on. That way, if something goes off the rails, you know exactly which step failed.
Next, we have routing. Routing is dynamically selecting the most appropriate path, model, tool, or subagent based entirely on the characteristics of the input. And this is desperately needed. Different tasks require entirely different domain expertise. If you have a fixed workflow, you're either going to overuse really expensive resources or you're going to underperform on specialized tasks. You definitely don't need your heaviest, most expensive reasoning model just to answer a simple hello, right?
There are actually a few different types of routing we can use. We've got input-based routing, which analyzes the user's input, tool routing for selecting the right API, model routing to optimize your cost and performance, and agent routing, which is all about delegating roles. You can logically route simple tasks to lightweight models just to save compute or specifically trigger a web search pipeline for current events while sending a complex math question to a symbolic solver. It's a real game changer for making the whole system dramatically more efficient and accurate.
Then there's tool use. This extends a system's capabilities to interact with external functions, APIs, databases, and the real-world environment. Without tool use, an AI relies completely on its outdated pre-training data.
But by explicitly invoking APIs, it becomes a dynamic coordinator capable of taking real action. This is what bridges the gap between knowing something and actually doing something. Whether it's querying a database, performing a calculation, or executing a financial transaction, tools turn intelligence into operational execution.
The last pattern here is reflection. This is about enabling a system to evaluate and improve its own outputs through iterative self-critique. It acts as an automated quality control loop. The agent can catch its own hallucinations and refine its work without ever needing human intervention. Before it returns an answer to you, it basically does a secondary check. It asks itself, wait, is this factually correct? Did I follow all the constraints? It mimics how a human would revise a rough first draft on the fly.
Now, armed with these patterns, developers face a major structural choice. So let's dive into Section 4, Single versus Multi-Agent, the great architectural debate.
Here's the crucial trade-off. On one side, we have single-agent systems, or SAS. These offer unified reasoning, full context preservation, and they are generally simpler and much easier to maintain. The model sees the entire problem context at once with a single uninterrupted train of thought. On the other side, we have multi-agent systems, or MAS. These offer distributed orchestration and structured decomposition, but they bring a lot of coordination complexity. You're breaking the problem apart and handing pieces to different worker models. It sounds amazing for specialization, sure, but it introduces some massive hidden costs.
Welcome to the reality of the coordination tax. As you scale up a multi-agent system, you run into significant challenges. First, the coordination tax itself. Message passing introduces information loss and overhead. Then there's the token budget. Your compute gets split across multiple agents, which actually reduces your reasoning depth. And finally, error propagation. Mistakes can amplify across the multi-agent pipeline. Every single time Agent A has to summarize its work to hand it off to Agent B, nuance gets lost. And if you have a strict compute budget, splitting it means your agents are acting way faster, but their thinking is much shallower.
Which leads us to this quote from the source material. Under equal thinking token budgets, single-agent systems often match or outperform multi-agent systems on multi-hop reasoning. This is a massive insight for how you should think about compute. You really should start with a single-agent baseline. Only escalate to multi-agent when your tasks strictly require parallel exploration or specialized decomposition. It's so tempting to jump to a multi-agent setup because it feels more advanced, but for deep, tightly coupled logic, a single coherent reasoning process is often much more reliable. Multi-agent is fantastic for highly decomposable tasks, like software engineering, where one writes code and another tests it. But for sure, it shouldn't be your default for everything.
Finally, let's explore Section 5, Memory, State, and Control, taking us from stateless execution to persistent intelligence.
To make sure your newly empowered employee actually remembers what happened in yesterday's meeting, you have to explicitly choose your memory structure. We're looking at two main approaches here. First is vector memory. This is embedding-based semantic retrieval, ideal for fuzzy searches and grasping concepts, like remembering the general vibe or meaning of past conversations. But then we have file-based memory. This is a log-structured document memory, which is perfect for exact historical state and temporal updates. If your agent is managing a complex project and needs to know exactly what was decided at 3 p.m. last Tuesday, you need file-based memory. A truly robust, evolving agentic system often employs both.
As we wrap up this explainer, I really want to leave you with this thought to chew on. Take a hard look at your architecture and ask yourself, are you building an agent or just a really long prompt? Are you truly building an adaptable, stateful system, or are you just hoping for the best with static inputs? Building real AI agents isn't about stringing together clever sentences. It's about composing patterns like routing, tool use, and reflection into an architecture that can actually perceive, act, and course correct. Start simple. Control your state, design for failure, and watch your AI transform from a passive consultant into a dynamic, reliable partner.